first day. Sessions that set the scene, reinforced the needs for monitoring, and we've heard a number of case studies, a number of issues with monitoring and reporting methane. Today we're going to continue with sessions looking at some real-world experiences of monitoring, and then some sessions looking at the newer technologies that are coming along. And we're going to end up this afternoon with a panel session looking at some of the future issues. I thought I'd just take the opportunity this morning, because I know a lot of people are probably going to have to start running off to the airport with all of the issues, just to thank everyone who's helped organize this. Thanks to the scientific committee who helped put the program together. Thanks to the audio guys who've been dealing with a lot of technical issues. Thanks to everyone who's turned up to listen. And particular thanks to my colleague Anne-Marie, who has helped put this all together, has organized everything, and has helped put the schedule together. So thanks, Anne-Marie. And now I'll hand straight over to David, who's going to chair the first session.
Good morning. I'm Dave Lowry. I'm a co-founder of the Greenhouse Gas Laboratory at Royal Holloway, University of London, many years ago. But for the last 10 years, I've been mostly focusing on mobile greenhouse gas measurement. So let's move on to the first speaker. That's Cindy Verhoeven from The Sniffers. Cindy is the regional business manager for The Sniffers and is responsible for much of the northern EU area. So over to you, Cindy.
What about now? Yeah. Good morning. There it is. So yes, I'm going to share some general experience that we have as a service company in reducing emissions. So it's not a case study, but general experience that we've had over the past 30 years in reducing emissions. So the Sniffers is an environmental service provider. We provide leak detection and emission management programs and also focus on pipeline integrity. And so as mentioned, we've been doing this for 30 years globally. So we have some experience to share. And basically, we discovered in the past years that there was a lot of focus on methane as a greenhouse gas, and it also caused for our company a big change and a shift in clientele. But it was also quite special to discover that something that we have been doing for such a long time was new in another part of the industry, in the gas industry. So driven by ambitious company targets, by industry guidelines such as the OGMP 2.0 framework, and also upcoming regulations that really drives the attention for methane. And it is great that we could share our experience and philosophy in that matter. So our philosophy has always been to build a detailed inventory of all your potential leak sources first. So to have a deep understanding of your installations, all the components, the properties of those components. So we pay a lot of attention in that area. And once we have built that inventory and performed baseline measurements, the initial measurements, then we build a multi-year plan to improve further over time. And we want to keep improving, so not just in the first year when you start to measure, but we also want to keep driving results by improving over the years. So after 4 years of measurements, you still, as a company, need to have the idea that you're achieving something, that you're improving. Otherwise, the attention for the results will go away. And that's also what we see, that then typically, if companies start to let go, the emissions go up again instead of down. So we keep driving those results by adding new technologies to the mix, looking for higher accuracy, lowering repair thresholds, and in the end what we also see is benchmarking and comparing results that typically drives long-term results. So how do we achieve that? Oh, I can also look in the front, that's convenient. So we basically have, I identified these 7 key success factors in long-term results, which means first of all focus on regulations and industry standards that are there. Luckily, more and more standards and regulations are being developed. So we built a leak detection and repair protocol, a multi-year plan that we incorporate in software. Company targets are incorporated, and we build a plan based on that. Then, as mentioned, the inventory of sources. Build a measurement scope, so that really means defining in detail every year what you are going to measure and when, taking into consideration stops, turnarounds. So it's really one program that ticks multiple boxes, but it has to fit. What we also see is better results if you combine measurement technologies. I'll come back to that later on. And then, of course, yeah, it's people. So have dedicated people to perform those measurements and process the results. So it's not a side job. It is really, if you are committed to reducing emissions, it is a day-to-day job and you need to focus on it. Forget about Excel. So use software, dedicated software to manage all your emission data. It's not something that you can do in SAP or in other systems that are already there because they're not built for that purpose. So having a dedicated software is really a success factor, especially if you're tracking targets and following up on repairs and looking for those long-term results. And then it's keep optimizing. So it's emission reduction. It's not a project. It's not even a program. It's a process, and you really need to understand that it's a multi-year process that you can keep improving over time as technologies develop, as software develop, as you start to integrate more and more, getting information out of different systems. And all with one purpose is emission reduction. So 3 basic steps. So I would like to focus now a little bit on the fugitive emission side. But basically, these 3 steps also apply to any emission type. The approach is the same. So it means attention in that first preparation phase. Identify the sources. We do that by, I'm not sure if by really identifying the applicable process streams on the technical drawings, on the P&IDs, and building that database with an overview, but drill down capability on a source level. So that means each individual component, flange, connection, valve, seal, has its own identity and properties in a database. Second, the measurements in the field. So you choose fit-for-purpose technologies. And it doesn't really matter which emission type you measure, whether it's vents or flaring, incomplete combustion, or leaks, fugitives. You choose measurement devices that give you the right sensitivity and accuracy that you are looking for. Again, based on company targets, protocols, and regulations. And then lastly, it's of course the result. So make sure that the reporting that you do is based on measurements and not on general leak rates, because then your results of your efforts in the field are never visible. And so how do we select those equipments, those measurement technologies? So what I'd like to demonstrate here, and basically my slide was not long enough because I can add an E, F, G, H, and I and go on. The message is it's okay to start out with one technology. For example, an optical gas imaging camera, and you screen and you find leaks. But you're also missing leaks, and you're not finding everything. And it's only applicable in certain circumstances. And if you add other technologies, not just for quantification, but also for leak detection. So if you use a camera for leak detection, but use another quantification device afterwards, you're still not finding all the leaks. So you really need to focus on both leak detection sensitivity and quantification accuracy. Those two things are important. Yeah, and then, so I stopped here at D, but there is also aerial-based measurements, fixed sensor technologies, all newer technologies that are not yet processed in the industry protocols and regulations that are there, but they are out there and they are improving every day. So definitely take those into consideration. So I'd like to focus now on emission calculation based on the source measurements. So these are the most applied techniques right now for leak detection and repair programs. FID measurements, and we have EPA method 21, or in Europe the EN 15446 standard, to convert ppm values that you find in the field into a mass loss in kilogram per year. And we do that by using factors. Even with optical gas imaging, so if you use a camera, it's not a measurement at all. It's only visible if a source leaks or doesn't leak, but you can still perform an emission calculation. And initially, this is okay. But you also need to understand that your calculation is very inaccurate and that you're also missing leaks. That is the main point. What we see in our experience is that all of these factors that the industry uses worldwide, they were not developed for methane, not at all. So what we see is that they give a large overestimation of fugitive leaks. So we see that the industry, what we feel the industry needs is a new development of methane-specific correlation factors. Because let's face it, in the field you keep measuring ppms and you keep screening with OGI cameras, but the factors don't match the actual results. And how do we measure the accurate results? With high-flow sampling, and we perform thousands of high-flow sampling every year. So we see these deviations, and I'd like to share. Oh, yep. These are some typical results where I have indicated the losses calculated with the factors. And in the last column, the actual loss that we measured with bagging the leak, which means measuring actually directly what's coming out of a leak. And you see here the big differences. So typically, these are not really exceptions. In 85% of the cases, it's an overestimation between 15 and 25, a factor 15 and 25 in the end result. So definitely something to consider. Here you see some examples of what the bagging looks like. So you actually wrap an equipment, measure the flow and concentration, and you know the molecular mass, temperature, and you calculate the actual loss. Oh, can I go back? Yeah. So for that purpose, we have built our own high-flow sampler. The original one was developed in the early, I don't know, 80s, 90s. Anyway, a long time ago when I was young. And the device was discontinued. Right now there are several of these new bagging devices on the market. We really needed them, so we decided a couple of years back to build our own. And it's right now based on more modern technology, so connectivity with software, again, having an audit trail so that you can trace back every measurement to the original source. How do we build a measurement scope and a measurement plan? So how do we mix those technologies and make sure that we know what we are going to measure every year? So this is an example of what we've been doing a lot in the past years. So initially, we start out with 100% inventory of sources. And again, an inventory is not an inventory. It can be done in 100 different ways with a lot of granularity and eye for detail, incorporating properties of each source, even the brand of a valve to monitor performance over time, etc. So you can do this in many ways, in the field, but also based on the P&IDs, on the technical drawings. And depending on how up-to-date all the information is, yeah, that also defines how accurate and up-to-date your database will be. Sometimes in parts of the world, technical drawings are not even available. So you need to go in the field and take pictures of each equipment and add numbers. It can be a lot of work, but it's also something that we've optimized and automized. So it can also be fairly quick and accurate at the same time, depending on the information that's available. So typically we perform a partial measurement in detail, meaning FID measurements and high flow sampling, just so you have an eye and an overview of all the leaks that are there, big and small. Sometimes there are not so many big leaks, but we find hundreds and hundreds of small leaks, and they add up also. So, and if you are using only a camera, you're also missing both big and small leaks. So that's why we mix these basic technologies always. Everything that you cannot measure, meaning everything that's not accessible or that's not in your detailed plan, you screen with a camera or you apply another methodology to make sure that you do measure the emissions and capture the emissions, or in any case, big problems that are there in installations. If it's a big installation, yeah, you can divide the installation in units. But in our gas transporting and distribution network, we also have thousands of small installations. There we measure a part of the installations and we develop a specific emission factor, for example, for a typical kind of well site or a typical kind of valve station or metering station, and we extrapolate those results over the parts that we don't measure, but screen with the camera. So in that way, we develop a multi-year plan. And to manage all that, we have developed a software, basically also grown over the past years. So we started out with the software that we developed to manage our own data as a service provider. And right now it's a tool that we also offer to companies to manage all emissions. So not only fugitives, but because you can calculate emissions based on factors, direct measurements, indirect measurements, source-based and site level, you can build your total emission number based on this hybrid calculation. Yeah, and it's also a tool to track leaks, monitor targets, and have some more detailed insight. I see my time is up, so that's basically all I wanted to share with you. And I believe a question session is after 4 speakers. Thank you.
Okay, thank you. Is that on? Thank you, Cindy. Our next speaker is Peter Evans from BP in the UK. Peter is a senior product owner for methane measurement and reduction, and his role is to identify, test and support deployments of new technology that underpins AIM4, and that's to install methane measurement at all the major gas and oil processing sites. Thank you, Peter.
Right. How are we on audio, folks? Good stuff. Oh, we've jumped on several slides already. Oh, right. You get the sneak preview. There we go. Okay, so the rate of change in this subject is quite remarkable. That if you look at where we were probably the last time that this conference was able to meet face to face, the topic of conversation was really, well, why should we reconcile methane data? And in the time it's taken us to have one small pandemic, we've gone from why should we be reconciling data and doing this extra work into how can we take these measurements and the technologies that will fulfill this part of an industry expectation and regulatory requirements into what is actually the important thing, which is what is this data telling us and what can we do with it? because when we're talking about reconciliation, yes, it is important that we are taking these measurements to improve the quality of what we report, be it to our regulators or our other stakeholders. But it's more important than that. The question is not just the quality of the reporting, but how can we use that information to manage our emissions more effectively, and in the case of methane, bring those emissions down. And we're moving into that phase. And what I would like to do today is present to you some results from 2 of our early deployments of top-down reconciliation work and comparing it to what we would report, where not everything is fully understood at this stage, but that's okay. When the OGMP was writing its guidance for this kind of work, it was quite clear that this is a process of inquiry, a process of investigation within which each piece of measurement that we do should inform the next generation of measurement that comes after it. And the language within that guidance is very much about one of continuous improvement, of continuous investigation to move forwards what we are doing as an industry based on that data. And in that spirit of transparency, what I'd like to do is present to you 2 quite different results from 2 of BP's operated assets, about as different as you can get within the ones that we own and operate. One of them is Clare Phase 1. It's to the west of Shetland in the cold, dark waters of the North Sea. Offshore, of course, and then the second is a large gas processing site called Sangashal. Sangashal is on the banks of the Caspian in Azerbaijan, managing the sum total of all the oil and gas that BP produces out in the Caspian and exporting that down into Europe. And in the climate in which we live, this is one of the main arterial routes of gas into Europe, and so the emissions that come from these facilities really matter, and managing these facilities really matter. For the purposes of reconciliation, these are single standalone units. They can be considered as populations of 1, and we need to be reconciling them at the individual asset level. And that reconciliation is only as good as the reported data that goes into that level 4 measurement in the first instance. And we start with understanding what is actually coming from these facilities. And if you look at the emissions as we understand them today, the vast majority of methane that is escaping to atmosphere is actually coming from processes. They are coming from flares, and they're coming from combustion sources. And for these sites, the fugitive emissions are a relatively small percentage. So on a materiality basis, it is these process variations which dominate. And when we're talking about reconciliation, we are targeting temporal differences in emissions that, we had a great presentation from Melin Turles and colleagues yesterday where you're talking about the onshore US, and there the question is reconciling over large areas of land and large numbers of dispersed assets, and it is a spatial challenge as much as anything. Here it is a temporal issue that when you're reconciling, you've got to know exactly what was happening on your facility at the moment in time with which you are comparing it with your level 5. And that matters because when you look at what happens on these sites, the emissions change by orders of magnitude over the course of the year. If a piece of equipment suddenly trips and you go into a flaring situation, the emissions can be 10, 100 times larger than they are when you're at steady state. What is also interesting, though, is when you look at the split of these emissions, these are very different facilities, but the relative proportions are roughly the same. The methane intensity, though, is quite different. That there's an order of magnitude difference between Clare, which is mostly an oil-producing facility, it doesn't actually produce that much gas, and Sangashal, which is predominantly a gas-producing facility. So when we're talking about methane intensity as well, these are very different sites in terms of the total amount of methane passing through them. So how are we taking these actual measurements? Well, Stefan Schweiter yesterday gave an insight into part of this technology, and colleagues from CCOPS will be talking about some of this later on today as well, that in an offshore setting, the principal technique that we are deploying is putting a spectrometer on an autonomous aircraft. I don't like calling them drones because they're a little bit more intelligent than that. You know, they're managing their own flight path and managing their orbits around the facility. The benefit of this kind of technology is twofold. From an operator's point of view, we're not putting a person on board. We're not sending people out in aircraft routinely. We are limiting the number of people that are having to transit between a site. So from an operational point of view, there are advantages that come from that. But also, from a data management point of view and from a reconciliation question, it is increasing the independence. That measurement is not being conducted in close communication with the asset. It's been being managed independently of what's happening on that site at the time. The downside to it is you have reduced levels of spatial resolution because you're taking everything from the facility simultaneously. Onshore is a different situation. These are much bigger sites. Sangashal is about 2 kilometers long. And that's compounded by the fact that the site has very complex wind patterns, where you've got the Caspian to one side, you've got mountains to the other. And so the wind patterns are changing almost on a minute-by-minute basis. And the most practical way to get measurements for these sites is then to break them down into large operational parts of that site and take measurements therein, and then combine that data into a composite figure. And that's akin to this sort of functional elements type idea that the guys from the National Physics Labs were talking about yesterday. It manages the environment better, or it manages that type of environment better, but you have a more complex challenge then of coming up with this composite value, which is the sum of all the different emissions at slightly different times from different parts of the site. So let's get to the stuff that people really care about. What are the results actually telling us? Well, here's the example from Clare, and we have the reported value, which is based upon the measured flow rates of gases through the system combined with emission factors, and it comes in at somewhere around 20 kilos an hour. It's worth bearing in mind that in a global context, 20 kilos an hour is a very small amount of methane. The top-down method, the verification method, is coming in at a statistically insignificant, if I can get the words out of my mouth, 17 kilos an hour. There's a really good match between those two figures. And that gives us confidence that at that moment in time, what's coming from Clare is a fair reflection, or what we're reporting is a fair reflection of what's actually happening. And that meets the expectations of the OGMP for the purposes of reconciliation. But we have to go deeper. This is a process of inquiry. It's not a case of ticking a box to say that we are happy that everything's fine on Clare. What do we need to do to understand our emissions better beyond that point? And in this instance, because it's mostly process data driven, we can pull that information from our data management and look at exactly how much gas was going up the flare, look at exactly how much gas was being used for power generation. And in the case of Clare, at that moment in time, everything was steady state. The flare was running at a constant rate. We weren't switching between turbines. And so there is something in the data that we cannot explain that might account for some of the greater variation that we see in between the two data points. And the important thing here is that the top-down method is not better, it is different. The purpose is having two different techniques that you're comparing and using that to drive that process of inquiry. And what that takes us to means that we're probably going to have to understand the top-down technique even better. We've done a number of sort of controlled release experiments to understand the method of the technique, but there are steps further that we probably should go. But it also highlights the importance of knowing exactly what's happening on your flare, exactly what's happening on your turbines at that precise moment in time. The emission factors that we currently apply to these components are the rate determining step in terms of understanding the emissions from those important bits of equipment. And that's why when people like Jan Sandvik, who's talking later on today, where we're putting in methodologies that for the level 4 part of the equation, we can look at a minute-by-minute variation of exactly what emissions are coming out of those pieces of equipment. Sangershall is a slightly more complex case. When you look at the total emissions that we would have reported for that site during that period of study, it would come in at roughly 230 kilos an hour. Again, for the size of the site and the amount of gas it is managing, that is a very small amount of methane. The verification figure, the level 5 measurement, is coming also with a statistically insignificant difference. It's coming in at 267 kilos an hour. The two numbers are basically the same. At a very superficial value, you would then say that the requirements of OGMP have been satisfied. We have two numbers that are reconciled, the site is reporting accurately. But when you look at the detail of where we see those sources are coming from, there is a material difference between what's actually contributing. So relative over-reporting, in the flaring in this case, is being offset by relative under-reporting in the case of some of the combustion sources. And that's because we found that one of the heaters on the site needed some maintenance, and that allowed us to intervene and materially change the emissions as well as improve the quality of the reporting from the site. And that's important because we can't just do this superficial level of reporting. We need to be using it as a process of understanding what is happening on the sites in order to inform our operations going forwards. And the challenge then comes to bodies like the IMEO as they're being stood up. They're built to receive the headline figures, but they need to be appreciating the implications of those figures and where it's taking us as well. And managing all of that contextual data is arguably as important in some cases as managing the headline figures that are coming off the measurement units. So reconciliation is an important part of the reduction process. It's so much more than just basic reporting. It's driving our operations to where they're going to have the most impact. Where should we be putting resources into managing our emissions more effectively? You have to have high quality data. You have to have good quality bottom-up data from all the different systems which have a material impact on your emissions, which means really good data on the flares, really good data on the combustion sources. And as we understand them better, we'll probably be having to get more into the fugitive space again and understanding that more. It highlights the importance of the need to interrogate the method and the results. As I said, the top-down and the bottom-up techniques are not better or worse, they are independent. And it's the power of that independence that drives the changes that we need. The big challenge to the IMEO then is how do you amalgamate all the results from different operators using very different methodologies in order to derive the results. And I know I'm a stuck record on this, but the best way that we can get after that is having clear standards for measurements so that the regulators, as they stand up, know what they're getting without having to have detailed conversations with us about each and every measurement that we've taken. And then the last piece for the operators is transparency. This will only work if we are prepared to put into the public domain, not just the Claire type results where everything looked fantastic, but also the results where there are questions to be had. Because where the questions lie is where the opportunities for reduction are probably at the greatest. I think I've done this with 5 seconds to go. So there you go. Thank you very much.
Thank you, Peter. Our next speaker is Hossein Maazallahi from the University of Utrecht. Hossein has recently submitted his Ph.D. thesis on mobile methane measurements and quantification and continues there to do his research. Over to you, Hossein.
Good morning. Can you hear me? Yeah, I can. I think so. The last time I presented a campaign, mobile measurement campaign in Hamburg, we had a couple of mobile measurement campaign in Hamburg, and this is a follow-up of the previous campaign we had. So we performed the mobile measurements in Hamburg, and this was the result, the map of Hamburg. You can see on the north side of Elbe. So this is the Elbe River, and this is the polygon indicating the residential area of the city. And then we drove around the city to find the peaks. We got the peaks. Not all of the peaks were from the same source. So we used the ethane and CO2 measurements to attribute CH4 signals to microbial, fossil, or combustion from cars. And the focus was on the fossil emissions. Fossil emissions means emissions from natural gas pipelines. But then some of the locations had a really high emission rates. So we had discussions with the suction team. Suction teams are performing measurements in Germany, and they provide data to the national inventory in the country. So we had a couple of meetings and discussed why there are some locations with really high measurements from mobile technique. So we designed a campaign again in Hamburg, and we performed the techniques at the same locations with mobile method, suction method, and tracer method as an independent technique, which has a lower uncertainty. So the first step to accomplish this campaign was to perform the detection, the leak detection. To find the leaks, we performed two methods. Leak detection from the mobile method and leak detection and confirmation from carpet method. Carpet method is the method people go on top of the pipelines. They have the map, and it is performed by the gas utilities. And then when we have the locations, we perform the techniques, the mobile method, suction method, and tracer method. And then we have the results to compare the quantifications. So when we perform the measurements, we notice that the emissions come from the outlets, which can be any of these outlets in the city. They can be from manholes next to a tree, or from the soil, or manhole in the middle of the street, or from side of the street, or again next to the tree, or from the cracks on the curbs next to trees, or from the cracks between the cobblestones, from rain drains, cracks in asphalt, the hydrants cap, a vent, there are some vents in the city. It can come, the emissions from the leak on the pipeline can come from the vents, or it can come from the telecommunication covers or gas caps. So basically, and then this one is an example where the company dig the locations to repair the leak. And then this one is one of the locations which was repaired. So emissions occur on a pipeline, on a leak at location A, but it comes out of ground on location B. Location A is leak location, and location B is outlet location. This is a difference that we need to be careful about. We're going to talk about it. So once the mobile method got the indication that there is a leak in this neighborhood, then carpet method performed their technique and applied drilling. They drilled, and they measured the concentration, and then they mapped the concentration, and the leak was boxed in between the highest concentration. So the leak was here. So this is one of the locations. And then once we know the leak, then suction. This is important for suction method because they have to put their probes around the leak location. So we have the leak indication from mobile method, and confirmation comes from the carpet method. And then from the information comes from the gas utility. They categorize the leaks to the A1, A2, B, and C. A1, A2, B, and C are safety categories. Safety categories and emission categories, in principle, should be independent from each other. But then we're going to talk about it later. So once they have the leak, they categorize it into A1, A2, B, and C. A1 should be repaired immediately, A2 within one week, B within 3 months, and C depending on the repair plans. Yeah. So we have a basket with the locations. In this campaign, we got 20 locations. 15 locations were initially detected from the mobile method. 13 of those locations were confirmed as a gas leak location. And 5 locations were reported from the gas utility. But then those 5 locations should be from the B and C, because the A1 and A2, they should be repaired either immediately or within 1 week. So this is not, there is not enough time to perform the quantification. In the mobile method, we had two instruments, Picaro G2301 and G4302. Together, they gave us the measurements of methane, ethane, and CO2. The inlet was from the front bumper, same inlet. And then we performed the detection, attribution, and quantification. And we performed transects as many as possible at different locations. And then we had the tracer method. Tracer method, they released acetylene at one of the locations. This is one of the telecommunication shaft cover. Emission were coming out of the openings at this cover. And then the tracer method were performed either in a mobile mode or a static mode. And then we had the suction method. So in the suction method, they put props around the leak location, and then they pump out the air out of ground until they reach equilibrium. So then when they reach equilibrium, it means that there is no accumulation anymore in the ground from the leak. So everything is coming out is from the leak, so they can report the emission rate. Yeah, so this is the result from the mobile method. We had 20 locations from HH1 to HH15 initially detected from the mobile method and confirmed from carpet method, and then 100 to 104. These are reported from the gas utility. So these locations were only in B and C category, like B and C category, where those locations where repair could be done in 3 months or within a repair schedule of the gas utility. But then most of the locations in this red box were among the A1 and A2 categories. This means that these locations should have been fixed either immediately or within 1 week. And you can see, like in the mobile method, there is a difference between these two categories. So in the mobile method, we have a cutoff, and this cutoff is 10% of a methane background. If we consider 2 ppm methane background, so this is 0.2 ppm. So every signal we get less than 2 ppm is considered as a red dot, and we don't see them. So, and then we get quantification. The quantification from the mobile method for this category is between 0.7 to 7.8 liter per minute. And in this category, which could only be quantified one of the locations was only 0.7 liter per minute. So there is a big difference between these two categories. And then tracer methods were performed at the locations, and then you can see in A1 and A2 categories, the emission rate were capped to almost 5 liter per minute. And then in the other category, they were maximum 0.14 liter per minute. So there is a difference between these two categories. At some of the locations, we faced really large subsurface accumulation. So when there is a really large subsurface accumulation, it means that the suction team, they have to pump air out of ground for hours and hours. And if the leak is within the A1 and A2 category, so it means that there is not enough time to perform the measurements, because the leak should be fixed immediately or within 1 week. And so for this location, we performed the mobile measurements on the streets, and then we got some signals in this area. We checked the outlets, and this outlet here showed really good signals that this could be close to the leak location. And there was some signs that there was a pipeline here. So we performed the quantification, and then we released acetylene at this location, assuming that the leak was really close to this location. But then once the Carper method were applied from the utility, they didn't find any leaks here. They found leak 60 meters away, south of the street. And this is important. Like, it means that the accumulation has a minimum radius of 60 meters. And this is way too much to pump out air out of ground within a allocated time for the suction team. So for this location, the mobile method reported 1.9 liter per minute, tracer method almost 4 liter per minute, and suction method, they didn't have time to perform the measurements. And this leak was categorized in A1 category, so it should be fixed immediately. And this is the results of all the locations. So A1 and A2 category, you can see there are bigger than B and C category. So in the beginning, safety category and emission category should be independent from each other. But it seems that they are not. It seems that the safety category of A1 and A2, they are bigger emitters. And this is important because A1 and A2 categories, if they are bigger emitters, they should be fixed immediately. And suction team, which are responsible to report emissions to the emission inventory in Germany, they measured mostly B and C leaks. So this means that there is a low bias in emission report in Germany. Number two, we faced like a location with a really large subsurface accumulation. This is not really favorable for mobile method, because then there are different outlets, like 60 meters away, 10 meters away, 20 meters away. And then mobile method gets the different signals separated from each other. And the mobile method can report more than one leak, although there was only one leak. And then this is not favorable for tracer method. It also depends on the location, because if it is really large subsurface accumulation and the outlets are really far away from each other, tracer method should be applied at the different location to simulate the emission. This is also not favorable for the suction team, because they need hours and hours to pump all the air out of ground, and it is not practical to measure these type of leaks. And mobile detection method is fast. You just get signals, and then you know the neighborhood where the leak can sits around. and then you report the location to the gas utility, and then the leak can be found. But then for the quantification, the quantification method can be improved, because in the mobile method quantification, we use the maximum enhancement, and this maximum enhancement can be replaced by the plume area. Then the quantification method is not dependent on the instrument. And then considering distance in the equation can improve the mobile measurements method. My thumbs is up, so I would like to invite you to my PhD defense. My promoter is Professor Rockman. I recently submitted my thesis, and the defense is 27th of September 2020 in Utrecht. And this was one of the chapters in my thesis, and the other chapters were also related. Two of the chapters are from Hamburg. So if you would like to attend it in person or online, just send me an email, and we will see how it goes. Thank you so much.
Okay, thank you, Hossein. Our final speaker in this session is Clay Bell from Colorado State University. Clay has participated in over 50 emission detection tests at METEC, and one of his main research aims is to establish metric-centric testing protocols. Clay.
All right, hello. So, let's see how this works. So, Clay Bell from CSU. Thanks for everybody for being here and organizing a great conference. So, this work that I'm going to present today is motivated by three key questions. So, the first is, how do we qualify solutions for some of these new programs, reporting standards, and the like? How do we evaluate the detection limits of those those solutions and methods? And how do we understand the uncertainty with measurements made by these different solutions? So the work is part of the ADDED project at CSU, and ADDED is aimed at developing transportable controlled testing protocols and demonstrating if the controlled test results are actually reflective or indicative of field performance. So today I'm going to focus on mostly just the test protocols, and the fieldwork side is sort of in progress this year. So when we discuss testing solutions, and I keep referring to them as solutions, not methods and not technologies, because we're really looking at the combination of a sensor, how it's deployed and used, and the analytics. Right? Now, the analytics are a key component of a solution, since generally what we're interested in is outputs like a detection, an attribution of that detection, and a quantification estimate, kilograms an hour, right, as opposed to a raw sensor reading like a ppm measurement. So, for some context, I wanted to introduce how many of these sort of new solutions are working. And, you know, most of my work's been done for me by other people in the conference here and already discussed this a fair bit, so we'll keep it quick. But one key difference is that the traditional methods like OGI and Method 21 are really up close and personal with the emission sources, and a lot of these new approaches for measurement are typically measuring the emissions after some dispersion and some transport has occurred, right? So we're generally seeing kind of two types of solutions out there. So the first is really making in situ measurements, right? They're measuring the concentration, and that requires the sensor to physically intersect the plume or a open path sensor to kind of transect the plume. So examples are point sensors that are sort of surrounding the site and downwind, line-based sensors that are shooting sort of out towards retroreflectors, sort of at fixed positions, concentration sensors that are driven around in mobile labs, and different aerial approaches like the flux plane approach that's described by several of the drone solutions, modified one for the scientific aviation spiral and the like, right? So the other type we're seeing a lot of is sort of scanning or imaging techniques. And these basically are different because you're set back a little bit further than traditional OGI techniques. But in general, you're generating a 2D or 3D map of the plume by scanning. So examples can be, you know, an IR camera or a hyperspectral camera on a pedestal up there. You can have a sweeping laser absorption technique. So you have sort of a instrument that's scanning an open path sensor and producing a map or an image pretty rapidly of the plume, or many airborne techniques. So you can have a drone that's shooting a laser at the ground, measuring the absorption in a column underneath it, and performing a screen that way, making sort of like a flux plane approach, or a scanning LDAR technique similar to what Bridger Photonics uses, or imaging like Kairos Aerospace from above in the air. So when we're talking about, you know, setting up protocols for testing these things, we're really looking for a couple things, right? We want there's a wide variety of approaches, and we want to define a test protocol that enables many of these different unique solutions to be tested under a similar circumstance, similar comparable protocols, right? We want to do that in a repeatable manner, and we want to focus on the outputs of the solution, not the sensor, right? So, and then finally, we want to put together metrics, right? So we want a way to compare method A versus method B, the quantification estimate from method A versus method B. And to do that, we really want to evaluate and establish metrics that enable these comparisons. So at a high level, the testing is conducted single blind, right? So the performers don't know the locations of the releases. They don't know the emission rates. They don't know how many sources are there. That's all blinded information. So in general, the test center selects the emission characteristics to map out the performance metric that we're interested in. So this can be tailored to look at detection limits by running smaller sources, or quantification accuracy over a wider range of emission sources. And the testing requires solutions to report data to us, right? And it reports system outputs, not sensor outputs. So we're looking for attribution and a quantification estimate. And then basically the test center produces a analysis of those results, right? So the primary metric that we're looking at has been the probability of detection curve. So this basically indicates the likelihood that a solution is going to be able to detect an emission source of a given characteristic. So in this case, it's emission rate on the x-axis, but we can look at other x-axes or normalize it by something like the wind speed or other variables. So to produce this, we basically plot the false negative results, so missed controlled releases, and the true positive results, so found controlled releases, on the 0 and 1 mark. We run a binomial, usually log it regression to produce sort of the fit to that shape. Gives you an idea of what the likelihood at any given emission rate is going to be. And then we bootstrap that result to produce a visual indication of the uncertainty. So in this example, the curve tells us that this solution would find about 9 out of 10 emission sources that have an emission rate of 2 kilograms an hour, right? And by looking at the uncertainty, if we were to go to the field, we would expect this solution may find 10 out of 10, or it may find 7 out of 10 sources of that size that would be present, right? Based on other parameters that may affect that detection. Now, you know, when we look at detection and we're looking at solutions, you can, you know, the last figure I showed true positive and false negative results. So those are controlled releases. We can also classify the detection reports sent in by folks as true positive, so they found the source, or a false positive, right? They reported something was there when we had no controlled release that was running, right? Now, this is important and highlights the importance of evaluating the solution, because a solution can potentially do really well with the thresholds turned way down low, so they're basically reporting everything they think they see, but that may result in a high number of false positives. So typically, if you're going to deploy and test, a solution is going to have tuned those set points using ROC analysis or something like that to minimize the number of false positives while still producing an acceptable level of detection. Right? Now, if they produce a quantification estimate, we can also look at sort of the accuracy of those estimates. You know, we can look at those in terms of a relative error compared to the controlled release rate, or an absolute error. So how many grams per hour or kilograms an hour they were off. And we can start binning that data and producing box plots to look at how does that error change over different range of release rates under different wind conditions, different distances for the measurement, or et cetera, right? Now, in the top, we can also run a linear regression through those estimates. So this one shows a bias high of about 60%. You have to be really careful with linear regression because we're often seeing heteroscedastic results where the error is not independent of the emission rate, right? So linear regression can be misleading in that case. Now, if they produce a GPS coordinate and kind of localization or a bounding box of coordinates, we can look at the accuracy of that location estimate as well as the sort of precision of the bounding box that they're in. So now kind of jump into some results. So we've applied this to over 15 different solutions, including continuous monitors and survey techniques. Up here, we can see the detection curves from several different solutions. The two on the left are continuous monitoring. The one on the right is an aircraft survey technique. The emission rates during the testing of the continuous monitors, we went up to about 180 liters a minute. Unfortunately, that was restricted based on our test site's capacity, our capabilities, and we didn't quite go high enough for these solutions to reach a 90% detection rate, right? Now you can see in sort of the uncertainty band that, you know, we have a lot of data down here at the low end, and that's producing a nice kind of confident result there. We get kind of fewer data points up here. They found a couple bigger ones, they've missed a couple bigger ones, and we have a wider uncertainty in how that curve's going to behave, right? Now, over on the right, I've normalized the release rate by the wind speed during that particular pass of the aircraft. In this one, we had a much better idea of sort of where that detection level was going to fall, and we've kind of focused our testing there. And you can see that we got a really nice result with a high degree of confidence in sort of where that detection limit's going to fall. With quantification, so these are the same three solutions. So we've got two continuous monitors, different styles, an aircraft survey technique. You know, we can see basically the linear regression, we're running, this is in percent error, so it's normalized by the emission rate of the source. Some are, significantly high, right? So here, I mean, we're looking, this is 500%. This one goes up to 1,500%, which is a factor of 15 overestimate, right? And, I mentioned you have to be careful whenever you run a linear regression to estimate your bias, because that data is the error, the residuals are not uniform across the range of the results. So that linear regression can be somewhat misleading. We can start to see that in the box plots, right? We've got sort of a really high percentage error at really low releases, and as we get larger, we're kind of constraining that error a bit more. So, I think none of this would be complete without discussing the limitations and kind of caveats of controlled testing. So, a couple things are not all publicly, released test results are single blind, so you got to be careful about that. The second is, any of these results are going to be constrained to sort of what the environmental conditions that you encountered during the test were, and what the facility type or the complexity of the experiments were, right? Did you run multiple releases? Were there combustion sources present? How large is the facility? It's also limited to sort of differences and deviations in the deployment of the sensor, right? So how many sensors were deployed? What was the average distance of them from the sources? And, what were the settings in the software and their black box analytics, et cetera, right? So kind of in conclusion, I think establishing sort of establishing metrics first of all, and then also protocols to evaluate those is a first step towards a standardization of some sort, right, to develop a way for sort of regulatory acceptance or acceptance of measurements made by these techniques in new programs like the OGMP. That's all I have. So thanks, everyone.
Thanks, Clay. Could I invite the other speakers in this morning's session to come back to the stage for questions, please? Okay, thanks. Do we have any questions from the floor?
Hello, can you hear me? Okay, so I think I have two questions to Cindy. First of all, I think all presentations were great, and I think it's super unfair towards other sessions to set the standards so high for the whole day. So I think it was great to hear them. So I have two questions for Cindy. So you mentioned LDAR as a practice that is implemented because of the environmental reasons, but historically, and also it is still the case, it is mostly implemented because of the safety reasons. And my question is, do you hear often comments from your clients complaining that they cannot do something because of the safety reasons, or that there is some trade-offs between what they are doing for safety and for environment? And on the other hand, do you see the tendency that companies that have very strict safety standards, they also do better when it comes to the methane emissions abatement? And the second question related to that is, I'm really curious to hear what do you do with the data that companies insert to your software? So I assume that you can use them and analyze them, in order to improve your services. I think it's really great idea, and I think it could be really, interesting to see how the whole process and how the data helps you also to improve the services that you provide. And the question to Peter is, so I need to recognize that it's really unfair to ask policy-related questions to engineers, and now I'm going to ask a policy-related question. So you mentioned the facility in the Azerbaijan. I was curious because part of the Repower EU plan, there is a very tiny idea of setting this you collect, we buy scheme. The idea is that so the methane abatement around Europe could be used in order to increase gas volumes that are available to the Europe, which I think is really crucial now because of the energy crisis. So there were also a couple of articles saying that we could get some additional gas volumes to Europe because of the methane abatement in, for instance, North Africa. So according to your assessment, how feasible it is, or is it really a good idea that providing some financial incentives or technical support for these countries could really help? Or do you think that it's a myopic idea, it takes ages and just move on with the next idea? So thank you very much.
I'll let Cindy start.
What was the question? No. No, thank you for your questions. So indeed, originally LDAR was invented for safety reasons and health, air quality. But historically, we've always tried to tick multiple boxes with the same program because that makes it easier for companies to accept, and also to, they are intrinsically, they want to use the same program efficiently. So it is safety reasons for maintenance optimization. So if you indicate clearly these are your leaks and this is how you can prioritize repair because these are the biggest ones, and etc. And then also there is an environmental stakeholder. So the maintenance people typically want to know, where are my risks, where are my leaks, and which one should I fix first? And environmental managers, they want to know, but how much, how high are my emissions, and how spot on, how accurate are we? And then we have corporate management, they want to know, but these are our targets, are we on our way in reaching those targets? And by offering one software or one program that ticks all those boxes, that makes it more easy for companies to implement and accept. So, and that's also our experience, and companies are happy to implement and accept it because it really helps them not only for safe operations, but also to tick those other boxes and satisfy other stakeholders. So reporting to service all those different stakeholders, that's important. And that's what we take into consideration. And your second question, that's actually a very good one, because indeed, when you work in different parts of the world and under different regulations, you kind of figure out what works in a program and what doesn't work. Because unfortunately, there are also regulations in place, or it can also be corporate policies or standards that, don't have the optimal result. And it's great that you can have a very rich database where you can compare and figure out what is kind of the ideal balance between implementation and maintenance of such a program. There's also a cost component. On the other hand, you also fix leaks and save emissions, and there are intrinsically within companies targets why they want an LDAR program. But it's kind of you have to figure out what is the optimum, and that it also depends on the geographical area where you are, because the whole the type of infrastructure, the regulations are very different, for example, in the US compared to Europe. So what works here doesn't work in the US and vice versa, or in the Middle East. So you have to take that into consideration. Yeah.
That gave me a moment to think.
Yes. Go ahead.
So, never ask an engineer a policy question. Somewhere in the background, there's one of the company lawyers in his crypt having kittens at the moment. Implicit in your question is actually a critical point that comes out of everything that's going on in this conference, that not all facilities are created equal. And the emissions associated with different production sites around the world are different. And at an even more granular level, the equipment within those facilities are not created equal. And therefore, blanket emission factors which serves us well historically, are not the basis upon which you can truly differentiate one site from another. Be it opportunities to bring gas in from different corridors, or to give credit to them, or simply to change the mix in where in the world anywhere chooses to import gas from, can only be as good as the quality of the measurements that go into that decision-making process. Likewise, the policymakers, the regulators, the emergence of differentiated trading of gas prices is only as good as the measurements that go into it. And it's our role, I would say, in this community to get those measurements as good as they can be, as quickly as they can be good, in order to avoid misinterpretations of that data. Get those measurements right, and everything that you talked about and more is possible. In the current climate, the question is, how fast can we move? You know, this is a nascent area of measurement science, and we are trying to do systemic changes to the industry whilst there are very real short-term, near-term things happening in global markets as well. And both are important, but we need to recognise that they do operate on slightly different timescales. So I'm not sure if that answers your question, but what it does say is we live and die by the quality of the measurements. Yeah.
Okay, we have questions.
Hello, can you hear? Yeah, this is for Cindy and all the LDAR. A two-part question. First of all, you said you identified all the PIDs or technical drawings, and then identifying all the possible leak points on different asset types and whatever. So one, do you identify every single technical drawing for your clients? And then two, how much detail do you go into these emission points? Per se, we've identified one valve, and then how much detail do you have to go to achieve level 4 reporting? Per se, if you have one valve with X plug and bleed valves, or anything auxiliary equipment for that.
Yeah, good question, thank you. So indeed, we go into the highest possible level of detail. That means that, well, basically you can do two things. If you go in the field and you look at the actual equipment, you have the most actual situation. Meaning that if you look at a valve, it can have basically standard 4 sources. So you have a flange in, a flange out, and a stem and a bonnet. But there can also be a lot of auxiliary equipment attached or on that same valve that is not on the technical drawing. So the option 1 is build the inventory in the field, reflects the actual situation at best. On the other hand, if your drawings are not up to date, yeah, you have a discrepancy there. So typically the most detailed drawings are the window between the software and the actual situation. So it's ideally, and I know we don't live in an ideal world, but ideally everything needs to be up to date for the most accurate calculation. The second option is to build that inventory based on the drawings. At least then you have a match there, but then there can be a deviation with the field. What we typically do is, if we build the inventory based on the technical drawings, it's a faster process, it's less effort, it can be done completely in the back office. But we also see, for example, on the drawing, you see a valve, but you don't know what type and how many points. If we then go in the field and our technicians see, this type of valve looks like this, it has, instead of 4, it has 20 sources. A picture is taken, it's being communicated back through the software, and the inventory is updated to match the actual situation. So that's the second approach. But indeed, for the level 4, it means a source-based inventory, not an equipment-based. So you need to go down to the highest level of detail and granularity. So each flange, each connection, yeah.
I'll just grab it. I have a question for you, Clay. So at a site like the METEC site in Colorado, you can do quite extensive testing. I suppose you sort of allude to it in your presentation, that there are some caveats. And my question is, do you think there's a need for in situ testing of technologies sort of in the real site where they'll be deployed? Or do you think it will be, you know, we'll see a world where it's actually sufficient to do controlled testing at a site like METEC or equivalent?
Sure. No, so absolutely. I think that there's limitations with any controlled testing you can do, and I think that the second part of added is really geared at this question of are controlled test results and the metrics we produce there indicative of what you're going to see in the field in different scenarios. So, I mean, the current project is literally going after that question. I think the answer is no, they're not, right? Not in all cases, right? And I think they can be quite useful, you know, especially to understand things like the uncertainty in your measurement technique, right? So I've heard a lot of groups say, oh, we've done a controlled release, right? We did 700, okay? And start to uncover things like, you know, the error is a function of the wind speed. And you can only see that if you have enough data to really dive into that sort of multivariate analysis, right? You know, and then in addition, you know, I've been in the field doing this type of work as well, and you certainly see a difference between what the controlled test results are suggesting a solution's going to be able to find, or their measurement is how their measurement is going to compare to your, you know, your high flow measurement or something of that nature, right? Or your tracer measurement. And you go in the field and you find out, yeah, it's not the same. I think there's still value in it, though. You know, a lot of work has been done on modeling emissions reduction techniques like the MEAT and the FEAST models, and those require you to populate some performance curves of your solution, right? So I think in order to get a good guess at what those performance curves look like, controlled testing is an approach to do that. But you certainly need to confirm in situ in the field that you're getting the right result. Right? So.
Okay, we should wrap up fairly soon for allow some time for coffee break.
Okay, thank you. Quick question for Clay as well. Do you think it's possible to add a quantification limit to your metrics and not only a detection limit?
Sorry, I didn't quite hear. To add quantification metrics?
Yeah, quantification limit. You showed
a limit.
Limit of detection, and we have as well a limit of quantification. Sometimes we can detect but not quantify because the acquisition is not well done. And another one is how we can put a context in the detection limit, because it will depend on, for instance, the distance between the measurement and the source, the atmospheric stability, the wind speed, and the detection limit that you can observe on your test facility will be different in the real condition. And maybe we can define some metrics that can help to extrapolate what will be the detection limit in real condition.
Sure. So for the quantification side, you know, I think the importance of the controlled testing is you can run a range of releases from very, very small to very, very large. If you're doing quantification, I think it's important to understand how the solution performs at low emission rates as well as high emission rates, right? We've definitely seen differences there. You know, and then I think it's up to you as the solution or the user of the solution to establish your sort of lower quantification limit, if you will, in terms of what degree of accuracy is acceptable to you, right? So if you want measurements that are within a factor of 2, right, plus 100%, minus 50% kind of error bars, you might need to go out to, you know, a kilogram an hour or greater, or 10 kilograms an hour or greater to find that, right? So, but I think in terms of the control testing, you map the whole performance you see, and then you interpret the result, right? And then in terms of the detection side, you know, we do look at those other variables and their influence. It's hard to do that multivariate analysis, show a nice 2D figure that represents that. In the case of the aircraft testing, it looked really nice when we normalized the emission rate by wind speed, right? So we had kind of looked at just emission rate, and you know, you had a much wider uncertainty band, and then you know, I binned the data by different wind speeds and looked at it. But when you do that, you reduce the number of data points going into each fit, so the power of the data gets sort of more and more restricted, right? And then if you can look at sort of compound variables like that, emission rate divided by wind speed, so kilograms per hour per meter per second wind for your detection, then all of a sudden all of your data comes back in, and sometimes it behaves very nicely and you get a more constrained result. Not all the time. So.
A last quick one from Thomas.
Yes, I have another question to Peter. You mentioned very nicely now this tale of the reconciliations. But I'm wondering now what a company like BP is now doing with that. You alluded to it very clearly, and I see immediately that in your onshore asset you have this overestimation in the flare emissions, right? So there is apparently, compared to the offshore, yeah, there is. You probably have well, the flare technology. I'm not sure whether it's so different, but can you now use this data to actually improve the process of flaring and reduce the emissions on your company level? And the other thing was your combustion unit. You said you found out that it was faulty. Was it based on these measurements, or did you find it out in the, like basically in the process of this experiment, or was it really by the discrepancy or by this information from these two different approaches?
So I'll answer the second part first. I mean, that is a classic case where it is a component, the nature of where it was emitting from, which is the top of a tall stack, is not something that was routinely monitored. And the verification, the top-down measurement, identified something that we didn't know about. So it's basic maintenance. It's go and fix. Yeah? And that's part of that method of inquiry point about what you're trying to do with reconciliation, is it's pointing out things that require deeper investigation. I mean, in terms of where we're heading as a company, there's two things happening. One of them is actually to improve the quality of the bottom-up data. We've set this target to, by the end of 2023, install measurement systems everywhere. And that is the bulk of where the work is going at the moment. And a lot of that is really around moving away from emission factors for key bits of equipment to where we're properly measuring them and doing that high temporal resolution on the emissions. So the stuff we'll talk about, there's a presentation later on today about turbines. You know, it's by the second difference in terms of the methane that's coming out of the turbines. Same goes for the flares, as putting in systems where we understand uniquely what that flare is doing at every given moment in time, so that we are reporting on a almost per second basis on the emission rate and not relying upon generic emission factors. In terms of the top-down, what you see there in the presentation was development work, proof of concept work, but it doesn't stop there, of course. And the next round of deployments are already underway. And with each and every deployment, we learn more about our systems, and we have to feed that back into our planning process so it doesn't become static. So, you know, the next big milestone for me on this is the technique we used offshore in the North Sea. We're now in the process of doing every asset that we have in the North Sea in the space of 1 year, so we can reconcile our assets at the business unit level not just the facility unit level. The next flight is literally next weekend, you know, and it's that process of turning this into a routine deployment. My measure of success is the day when I'm no longer needed in the business, and where this becomes so routine and such a regular part of our routine operations. It sits into the same space as the firms that come out to do NOx and SOx testing, or people that come out to check on the calibrations on our fiscal meters, and at which point this is business as usual. I move on, and it's just a main part of what everyday life is like for the business.
Okay, thank the speakers again for 4 excellent presentations this morning. Right, so I think we're now down to 15 minutes for coffee break. Can I encourage everybody who hasn't had a chance to see the posters yet that we've got around the corner to have a look during the upcoming break and lunchtime? Thanks.